In today's class, I am going to discuss definition of rigid body, rotation of rigid body, moment of inertia, and kinetic energy of rotation. So, let us start. What is a rigid body? We take a piece of stone. We mark 2 points at position I and J. The distance between this point Rij. If this distance Rij remains constant throughout any condition, throughout any application of external forces, then we should call this body as rigid body. In more elaborate form, what I am going to say, the distance between every point should not change, then this body is called rigid body. If we apply force, if we apply other external means, the distance between two specific points should not change, then we should term this as a rigid body. So the definition we read: a rigid body is an idealized solid object where the distance between any two points remains constant. Now we consider the rotation of this body. We first take the rotation axis. Now there we place this stone in xy plane and it rotates through this axis with angular velocity omega. We take 2 point masses m1 and m2. The mass m2 is from distance r2 from the rotation axis and m1 is r1 apart from the rotation axis. Now the moment of inertia for mass m1 is I1 equals to m1 r1 square, and moment of inertia for mass m2 is I2 equals to m2 r2 square. We see the moment of inertia is mass times is square of the distance from the rotation axis. Now there is a standard notation. We consider counterclockwise direction as positive rotation and clockwise direction as negative rotation. Now this rigid body consists of several masses. We can imagine this body consists of m masses, and if we sum up all the individual moment of inertia of these masses, we get the total moment of inertia for the rigid body, and this is written explicitly: I equals to sum over I mi ri square, where I can extend from 1 to n. I want to say we consider this body as n number of point masses, then this will result total moment of inertia like this. Now moment of inertia, we first take the rotation axis and we place a object. We consider 2 points of this object A and B. Now if we want to rotate this object through this rotation axis, we should apply torque. First we apply torque at A, then this body will rotate about this axis, and next we apply torque at point B. These times this body will also rotate about this axis. Now which one is easier to rotate? Clearly at point A we need much torque than at point B. This is a practical example. Now suppose we want to open a door. We always push farthest point from the hinges of the door. If we push closest point to the hinges of the door, we have to press more. This is a practical example. So moment of inertia measures how mass is distributed relative to an axis of rotation. The further the mass is from the axis, the harder it is to rotate the object. For the case at point A, the whole mass is distributed away from this rotation axis, and to rotate this object we have to apply much more torque at point A than at point B. Now we will find the relationship between angular velocity and linear velocity. This is the rotation axis and this is the circular orbit through which this body rotates. Let at any point the linear velocity is v, and this orbit has a radius r. So the relationship between angular velocity and linear velocity is v equals to omega r. This is a scalar relationship. Now the kinetic energy for rotation. The body is revolving around that orbit with velocity v. So its linear kinetic energy is k equals to half mv square. Now we replace v by omega r. Then we get kinetic energy half m omega r whole square and half m r square omega square. Now this quantity m r square is the moment of inertia of that body. So we write k kinetic energy is half I omega square. So kinetic energy of rotation k equals to half I omega square. The moment of inertia, what is the physical significance of it? This is the resistance to rotation or rotational motion. And torque tau is the rotational equivalent of force. And we relationship torque tau equals to moment of inertia times its angular acceleration.